Okay, so the next one is an interesting one. So what do we have here? We have 0.25 kilograms of steam at 1 megapascal and 400 degrees C. Is initially filled inside a piston cylinder device made with a set of stops. So somewhere we have stops. The location of the stops corresponds to 55% of the initial volume. Okay. Now the steam is cooled, so we are rejecting heat. So the piston will move down. So we have to determine the compression work. So this is compression work. The piston is moving down, so dV will end up negative. So we are anticipating that we will have a work N, and therefore the work should be negative. So what is a compression work? If the final state is, first case, at a pressure of 1 megapascal and 250 degrees C, and B, the pressure is lower than the initial pressure at 500 kilopascal. And in this case, so when it's 500 kilopascal, we have also to determine the temperature at the final state. Okay, so this one will be problem 4.5. Okay, so let's sketch this. We have state 1. It's a piston cylinder assembly. We have the piston at its top position. It's filled with steam, but specifically in this problem we have somewhere a set of stops. Okay, so the piston cannot go below this level. So what do we know? We are given that P1 is equal to 1 megapascals, and we are given T1 is equal to 400 degrees C. And we are told that we'll be cooling down this, so therefore we're rejecting heat. And this will lead us to state 2. Where we will have the set of stops here, and the piston will move down. Okay, the point is that we ultimately don't know where is the piston at the end. Okay, so this is why we have two cases. Okay, and based on the final pressure, we will have to understand if the piston has reached the stops or not. Okay. So that's it. The only thing that we have also is that the mass remains constant between the two, is 0.25 kilograms. And we are asked to calculate the work in two conditions. The first one is P2 is equal to 1 megapascals, and we were given T2 is equal 250 degrees C, so this is case A. And case B, we are simply given that P2 is equal to 500 kilopascals. Okay, so let's go with the first case. Okay, computation of the work 1, 2. If as a final state we have P2 is equal 1 megapascal and T2 is equal to what? Is equal 250 degrees C. Something interesting here is that in the specific case, you see that P2 is equal to P1. So therefore, the process in this case is isobaric. So this makes our life much easier. The work 1, 2 is equal to the integral of 1 to 2 of P dV, which is equal to what? We said that the pressure remains constant. We like to write it in terms of specific volumes. So this will be the mass. Integral 1 to 2 of d specific volume, which is equal to what? Is equal m P1 or P2, it's the same, cross V2 minus V1. So if we get the specific volume, V1 and V2, we have P1, 1 megapascal. We have the mass 0.25 kilograms, so therefore we can get our work. With V1 is equal to the specific volume under the following conditions. P1 is equal to 1 megapascal, and T1 is equal to 400 degrees C. You will get a value of 0.3066 cubic meters per kilogram that you will get from a table, and you will find this as superheated vapor. So you will have to go to the superheated water table. And so this is for V1, and for V2, it's equal to the specific volume under the following conditions. We keep the pressure constant, P2 1 megapascals, and now we have a final temperature, T2 is equal to 250 degrees C. Same thing, you go to the table, and then you will get a value of 0.2327 cubic meters per kilograms, and it remains superheated vapor. Okay, and you can see that so V2 is lower than V1, which makes sense here. Okay, so finally, the work 1-2 is equal to what? We said it's equal to the mass cross P1 cross V2 minus V1, which is equal to, our mass is 0.25. Our pressure is 1 megapascal. You have to be careful. You have to convert it to kilopascals. So this will give us the 10 exponent 3. Cross, we said our V2 is equal 0.2327 minus V1 0.3066. And this would give us a work equal to minus 18.47 kilojoules. And as you can see, the work is negative, which is expected because here we have compression. dV is negative, dV is negative, so the work is negative. Let's move on now to the second part. In second part B, what we are told that we need to calculate the work, but if the pressure now P2 is equal to 500 kilopascal. This is a critical information, okay? So because the 500 kilopascal is lower than our 1 megapascal, right? Okay? So what does it mean and how we have to interpret this? This means that the piston moved down at constant pressure at 500 kilopascal until it reaches the stops. All this process here, while the piston is moving down, it's at constant pressure at 1 megapascal. If the pressure is lower, so which means that the piston has already hit the stops and we are continuing rejecting heat. And this is why now we have a lower pressure. So which means that having a final pressure P2 lower than P1, 1 megapascal, is an indication that the piston has already touched the stops, which is extremely critical for us because this will give us an additional information on the final volume, okay, of our gas, okay, of our steam in this case, because we are told that this actually represents 55% of V1, okay, and this will be critical information to solve the problem. So then, because we know that the piston is sitting now on the stops, so we know that V2 is equal to 0.55 V1, this is our 55%. We don't like volumes, so We'll write this in specific volumes. So V2 is equal 0.55 V1. Interestingly enough, we just got the value of V1. So therefore, we can get V2 directly. So then, the work 1, 2 is equal to what? It's still equal to the integral 1 to 2 of PdV. And it's equal to what? It's equal to M P1 V2 minus V1. Okay? Now you can see that I considered the process as isobaric, and I put the pressure constant and is equal to P1. Why? Because we can decompose the work here into two parts. The one where the piston moves down, okay, which is at constant pressure, exactly this term. Then when it hits the stops, the work is equal to 0, right? Because then our dV becomes 0. So therefore, there is no work after the piston reaches the stops, okay? So this is why we only consider, if you want, the work until the piston reaches the stops. So we have the mass, yes. We have the pressure, which is 1 megapascal. We have V1, and this one we know it is 0.55 V1. So therefore, we can continue and write P1 cross, this is 0.55 V1 minus V1. And this will give us minus 0.45, this is this value here, and P1 V1. And if we plug the values, so of the mass, the pressure, and the specific volume V1, this will give us minus 34.5 kilojoules, okay, of work. We are also asked to get the temperature, T2. So in this case, so the final temperature, T2. So T2 will be defined by what? It will be defined by the temperature under the following conditions. What do we know? We know V2 is equal 0.55 V1. And we know that the pressure P2 is equal to 500 kilopascal in the second case. So 0.55 V1, we calculated V1, so this will give us a value for V2 is equal 0.16863. And we will end up actually in the mixture phase, and the value for the temperature will be 151.86 degrees C, okay? So our value of V2 will end up between Vf and Vj at 500 kilopascal. So therefore, our conclusion is that the temperature will be the saturation temperature at the pressure of 500 kilopascals.